Hello, I'm Carmen Strassle, and today I'll be talking about a very well-studied problem, and that is the one of learning decision trees. This is joint work with fellow PhD student Caleb Koch and our advisor Leon Tan, who are both at Stanford in the theory group. So let's get started. In this talk, I'll be talking about an algorithmic problem that many of us are already familiar with, which is that of constructing decision tree representations of data. So the setup here is that we are given some labeled data, and we want to come up with a decision tree that explains the data set. This is a computer science classic. It's a very basic algorithmic problem. And for simplicity, we'll focus on the simplest setting, where we have binary features and binary labels. Though, of course, the problem makes sense and is well studied over all sorts of feature and label spaces. So decision trees are going to be the star of this talk. Let's spend a slide motivating them. So decision trees are perhaps the most canonical example of an interpretable model. In some ways, their reasoning works almost like human reasoning. And just as an example, for anyone who hasn't seen decision trees before, if we have some example input x equals 0, 1, 0, 1, well, here the fourth bit is a 1, so when we query x4, we'll follow the path to the right. The first bit is a 0, so we'll go left. The second bit is a 1 again, so we'll go right, and then we hit a leaf, which is a 0, so we output 0. So you can see that decision trees are very fast to evaluate. It scales with the depth, which is logarithmic in the overall size, the evaluation time, that is, and yeah, the thing is super interpretable. They're also the heart of powerful ensemble methods that are used loads in practice, and that's random forests and XGBoost. Well, we're all theorists here, so I won't spend too much time on practice. And in the theory, decision trees have been studied in the very early days of pack learning. There are very early pack learning results for this problem, and in fact, in this talk, we'll get to revisit some of these very early results in this field. As a complexity theorist, studying decision trees is especially exciting because they live in this really fun sweet spot where they're on the knife edge of tractability. In some versions of the problem, we can hope for tractable, efficient algorithms, and some versions of the problem we know are inefficient. So we can learn a lot from studying decision trees and figuring out exactly where they lie. In this talk, in this work, we focus specifically on constructing decision trees of optimal size. When I said in the previous slide that decision trees are interpretable, fast to evaluate, and so on, what I really meant was that small decision trees are interpretable, and small decision trees are fast to evaluate. There's some motivation for why we care about the decision tree's size being optimal. And so there are many ways to formalize this algorithmic problem. We will consider the most well-studied one, which is, of course, the pack model. Many of you may be familiar with this already, but for those who aren't, in this model, the learner is given labeled examples where F is a size S tree and X, these examples are drawn from some arbitrary distribution D. And the goal is to output a hypothesis H, which is the same size of the target and which agrees on the target on all but a epsilon fraction of inputs, or for an arbitrary distribution with probability at most epsilon, it errs. Here's just a visual of the pack model. Again, remember we have this target, which is unknown, and our goal is to output a hypothesis. So in the language of learning theory, this is properly packed learning decision trees. This is the model we're considering. And the word properly here means that we have to output a size S decision tree. It has to be the same size as the target. So there are many variants and relaxations of this problem, for which we have many different algorithms. But for this version of the problem, we just have one algorithm. And it's not even that interesting of an algorithm. We simply draw a bunch of data. In particular, we're going to draw S log n labeled examples. And that specific value is just large enough so that generalization bounds can kick in. It's just the VC dimension. And then we find a size S decision tree hypothesis that fits this data set perfectly. And the way that the algorithm works is essentially by brute force. So it's an algorithm that's been rediscovered many times. And what it does is, given a data set labeled by an n variable size S decision tree, there's a dynamic program that runs in time exponential n and returns a size S decision tree that perfectly fits the data. You'll notice that this runtime actually doesn't depend on S, so it's not strictly a brute force algorithm, because the true brute force algorithm would cycle through all size S decision trees, and so the runtime would be something like 2 to the n to the s. So the dynamic program does a little bit better than that, but I promise you it's still close to brute force. And a very natural question, which is the focus of many papers and the focus of our work, is whether this algorithm is optimal. In some sense, we've known the answer for over 30 years. And in fact, this is one of the earliest negative results in learning. And it's this, that properly packed learning decision trees is NP hard. Therefore, if SAT requires exponential time, then so does this problem. So what do we do from here? One route is to relax the requirement that the learner be proper. So instead of insisting that the learner output a hypothesis, which is the same size as the target, we can allow it to output a size capital S hypothesis, where capital S is bigger than little s. This relaxation of this problem has led to a fruitful line of work, many papers, including one that I actually have with these same co-authors, Caleb and Leong. So I'm happy to talk about that paper offline, but this is not the focus of this talk. Instead, we're going to change the problem in a different way. We're going to make it algorithmically easier in a different way, and that will make our job as lower bounds people a little bit harder and a little bit more interesting. So here's the problem that we consider. In addition to being able to receive labeled examples passively, what if we allow the learner to also make active queries to the target? The question we're interested in, which has been asked multiple times in the literature, is, are there efficient query algorithms? Or does the problem still remain NP hard? This is a nice question in theory, and there's also some nice practical motivation for it. This problem captures the task of converting an existing black box model into a decision tree model. Why might you want to do this? Well, remember, decision trees are highly interpretable. So if you have something that's completely inscrutable and you want to understand it for fairness reasons or scientific reasons, then it'd be great to have a decision tree representation instead. So this turns out to be a great question for a couple of reasons. One is that it reveals a huge gap in our understanding. So what do we know in terms of upper bounds? Well, the fastest algorithm is still this exponential time algorithm that I showed you a few slides ago that just uses dynamic programming. Okay, what about lower bounds? There are no lower bounds. So a truly efficient algorithm, a polynomial time algorithm, could be possible. So there is this huge gap where the fastest algorithm is exponential and there are actually zero lower bounds. So that's one reason that this is a good line of research to pursue. Another is because it opened the door to a lot of algorithmic progress. So there's been lots of interesting query algorithms that almost solve the problem. So I'll talk in the next slide a little bit what I mean by almost solve the problem. So the first class of algorithms are those that are not quite proper, in the sense that they output hypotheses that are generalizations of decision trees. So they'll output DNF formulas or small depth circuits, which aren't exactly decision trees. They're more powerful than them, so this algorithmic task is a bit easier. The other line of algorithms are proper, but they rely on distributional assumptions. So instead of these algorithms working for arbitrary distributions, they only work for the uniform distribution. So the natural question is, can we get rid of these distributional assumptions and make these algorithms work for any distribution? Or indeed, could we modify these other algorithms and allow them to output hypotheses that are actually decision trees and not generalizations of them? This is the focus of this talk, is whether we can do these things. And the answer is no. And in fact, this is the main result of our paper. So, providing a counterpoint to the algorithmic progress, we prove the first lower bound for this problem, showing that it's NP hard even for query learners. Therefore, if SAT requires exponential time, then so does this problem. In other words, if you believe SAT requires exponential time, then this dynamic programming algorithm, that's just a brute force algorithm, is essentially optimal. So just to restate our main result a little more formally, suppose that there is a query learning algorithm, that is one that's given queries to an n variable size S decision tree, where S is linear in n, and access to draws from the distribution. If this learning query algorithm runs in time t of n and outputs a size S decision tree that achieves error at most 1% under the distribution, then SAT can be solved in time polynomial in t of n squared. So in particular, if the learning task can be solved in polynomial time, then SAT can be solved in polynomial time. And if the learning task can be solved in sub-exponential time, then SAT can be solved in sub-exponential time. So a few remarks about this main result. There are very few NP hardness results for query learners, especially compared to the random example setting. The only other we're aware of is the hardness of learning DNFs, and it's this result due to Feldman. Our technique is entirely different from Feldman's, so this is a powerful learning model in need of new lower bound techniques. And our work adds to this very small arsenal. We also rule out learners that are allowed constant error. On the previous slide, I talked about a learner that achieves 1% error. This is why I'm able to do that. And existing lower bounds, even for random example learners, only hold for inverse polynomial error. So we have some improvement over those results. Finally, en route to our main result, we strengthen existing hardness results for another well-studied problem, and as hopefully I'll convince you later, a very highly related problem, which is that of decision tree minimization, which is a problem that's exactly what it sounds like. You're given a decision tree, and your goal is to output the smallest equivalent decision tree. So for the rest of this talk, I'll first talk about previous approaches for random example learnings and why we cannot use them to extend to the setting of query learners. And as a result, we'll need a new technique. So I'll give an overview of our approach. And we use this technique that we call hardness distillation, which allows us to convert the hardness of decision tree minimization into the hardness of learning. And finally, I will conclude with some open problems and future directions. So first, how did people prove hardness for random example learners? Well, they all start from the hardness of learning a rather simple concept class, disjunctions, the OR of variables. There's a rather simple and elegant reduction from set cover to this problem. I'm representing set cover here in a slightly unconventional way. The problem consists of a bipartite graph. On the right-hand side, we have universe elements, and on the left-hand side, we have sets. We have edges going from sets to universe elements, and the goal is to find a collection of sets that neighbor the entire universe. Neighbor, cover, hit, however you want to think about it. You can see here in red, I've colored in S1 and Sn, and together they hit the whole universe. So S1 and Sn form a set cover. This reduction from set cover to learning disjunctions has been the starting point for all previous decision tree learning results. So it's worth understanding. So how does this reduction work? We'll be thinking of sets as variables and universe elements as data points. So for each universe element, I'm going to define an indicator string, an n-bit string, which is the indicator of which of the sets contain u sub j. So this is best understood through examples. So the first indicator string for u sub 1 is just 1 followed by all zeros. Why is this? Well, if you look at u1 in the graph, there's only one edge going from u1 to s1. So u1 is only contained in s1, so the first bit of this indicator string is 1 and everything else is 0. What about u2? Well, u2 has edges going from s1, s2, and s3. So that's why u2, its indicator string, has 3 1s at the start, and then it's followed by zeros. So what's our target function? What is this disjunction that's we're going to show is complex? Well, it's this function called covered by opt-cover, and it is the OR of the sets in the optimal set cover. So in this example, it would be x1 or xn. And the reason for that is because S1 and Sn, the corresponding sets that correspond to these variables, cover the entire universe. So it's just an OR of the optimal set cover. So a couple observations about this construction. Covered by opt-cover, the all zeros string is equal to 0. Of course, it's an OR of at least one variable, it'll equal 0. And also covered by opt-cover of any universe element is equal to 1. Why is that? Well, if I'm taking the OR of all of the sets in the set cover, well, by definition, since it's a set cover, it has to cover all of the universe elements. And so as a result, since I'm hitting all the universe elements, they'll all be covered by the opt cover. So that's why that equals 1. Second observation, suppose you have an arbitrary disjunction that correctly classifies both the all 0 input and also each of these universe elements. Then this disjunction, this C, has to be a set cover. Why is that? Well, if you're correctly classifying all of the universe elements, that effectively means that you have to, quote unquote, hit every single universe element. You have to cover it. Therefore, C must be a set cover. These observations simply result through our definitions of covered by opt cover and through our definition of these indicator variables. So these two observations taken together mean that we have a connection between the size of the optimal set cover and the complexity of the target function. This is crucial for establishing a learning hardness result. So as I said before, the target function's complexity scales with the size of the optimal set cover. In fact, the target function is defined in terms of the optimal set cover. This is a problem for a couple of reasons. One, it's impossible to efficiently create this reduction as a result. We cannot efficiently provide query access to the target. Why? Well, in order to provide query access, we have to know what the target is. And in order to know what the target is, we have to solve set cover, which is, of course, an NP-hard problem. So this creates a completely inefficient reduction. Second, even if we could somehow efficiently provide query access, well, now the problem's easy for a query learner. All you have to do is simply query all the Hamming weight 1 strings, and you can pick out all the sets in the optimal set cover. Easy as that. So, as I mentioned before, all of the previous decision tree hardness results build on this, and hence they all suffer from the same limitation. So in our approach, we need the target to not be defined in terms of the optimal solution, but somehow its decision tree complexity should still scale with the value of the optimal solution. So how do we get around this pitfall in previous approaches? Well, instead of using set cover, we're going to use vertex cover, which is a particular case of set cover, so it's a bit simpler than set cover. And using this simpler NP-hard problem allows us to use a more complicated and a more expressive target function. This target function is called isEdge, and it's 1 if the input indicates an edge in G. And so instead of our target function asking, are you hit by the optimal vertex cover, it simply asks, does this string correspond to an edge in the graph? And you'll notice that this target function does not depend on the optimal vertex cover, but we are able to nevertheless show that its decision tree complexity does scale with the size of the optimal vertex cover. This is crucial in our reduction, and it allows us to circumvent this roadblock in previous approaches. I'll provide a little motivation for why we chose to reduce from vertex cover. So one is that this problem isn't just NP-hard, it is NP-hard even to approximate and even on constant degree graphs. We will rely on this in our proof, but I won't have time here to get to it in this talk. And perhaps more importantly, vertex cover is at the heart of hardness results for decision tree minimization. As you'll see soon, our proof rests on the connection between decision tree minimization and decision tree learning. So we will consider these two problems, one being that of learning decision trees and the other being that of decision tree minimization. And we relate them with this process that we call hardness distillation. So to remind you, in decision tree minimization, it's exactly as it sounds. We have a decision tree, and our goal is to output a small equivalent decision tree. And how does this compare with decision tree learning? Well, in decision tree learning, we're given queries to a decision tree, and our goal is to output a small, high accuracy decision tree. So how do these problems compare? Is one easier than the other? Well, strictly speaking, they're incomparable. In the learning setting, we have less access to our target. We can't look at the whole thing. We only have query access. But we also trade that in for a weaker assumption on the output. So instead of demanding an equivalent decision tree, we only need a small high accuracy decision tree. So it's allowed to err a bit. We'll see, though, that with hardness distillation, we'll be able to unify these two problems. So here's the three-step game plan that will take us all the way from decision tree minimization to the hardness of learning decision trees. So first, again, we start with decision tree minimization. Our goal is to output a small equivalent decision tree. And we're going to make this problem a little bit easier algorithmically. So instead of requiring the algorithm to fully agree with T on the entire domain, now we just have this small set of inputs, D, and the decision tree T prime only has to agree with T on this small set of inputs, D. Now we're going to make the problem even easier algorithmically. And so we instead of saying that the decision tree has to agree with T on all of this hard set of inputs, D, now the decision tree only has to agree with T on 99% of D. You can see that the algorithmic problem is becoming easier and easier, and hence hardness results become harder and harder to establish. We call this process hardness distillation. As you can see, we're sort of homing in on the hardness of decision tree minimization. You can think of D as a sort of hardness witness. It's a small set of inputs over which it should still be difficult to find a small T prime that agrees with T. So to recap, this is step 3 of the hardness distillation process, where now our decision tree T prime only has to agree on this small set D with 99% accuracy. And you can hopefully see that if this problem is hard, then decision tree minimization is hard. But in fact, maybe you can also see that if this problem is hard, then learning decision trees with queries is also hard. Our hard target function is T, which of course we can provide query access to because we can see the entire function T. And our hard distribution is uniform on this hard witness, which is this small set D over which the tree is still hard to learn, even if we allow some error. So that concludes all that I'll say about our techniques. Quickly, I want to recap our results and mention some open problems. Again, in this talk, we focused on the proper setting, where we want to construct hypotheses which are the same size as our target. So, as I said before, the best known algorithm is this dynamic programming algorithm that runs in time exponential in n. And we have this very old result from the early days of learning theory, which is that this algorithm is optimal for random example learners. And in this work, we showed that it's also optimal for query learners. Now, one way to relax this is to give an easier task. And instead of saying construct a hypothesis of size S, we can say construct a hypothesis of any size. In that case, it's an easier algorithmic task, and so the best known algorithm is more efficient. It's due to Ehrenfeld and Hausler, and it runs in time n to the log s. And under a complexity conjecture, this algorithm, Ehrenfeld and Hausler, is optimal for random example learners. And this is a paper from this year with actually these same co-authors, Caleb and Li Yang. So if you'd like to talk to me about that, I'm happy to talk about it offline. So what's open is, what about query learners? Is the Ehrenfeld-Hausler algorithm also optimal for query learners? Or can queries allow a learner to circumvent the lower bound against random example learners? Another open line of work that I'd like to talk about is the effect of distributional assumptions. So you can think of distributional assumptions as existing on an axis. In this work, we had no distributional assumptions. The algorithm had to work against any arbitrarily complex distribution. And we showed that under this assumption, the problem is NP-hard. And as I alluded to a bit earlier in this talk, if you increase the distributional assumptions all the way to assuming that the distribution is uniform, then there is an n to the log n time algorithm. So one might ask, how does the complexity of the problem scale with the complexity of the distribution? If we, for example, made weaker distributional assumptions than the uniform distribution, could we make some algorithmic progress in those settings? This is a problem that's been explored recently by my co-author and advisor, Liang Tan, and a few other students. And they've made progress for a few first steps, but there's still much more to be done. And in general, this is a fairly unexplored question. So that's it for me. Thank you so much for listening.